Okay, we are recording, so the floor is yours.
Okay, great. Well, thanks everyone for coming. This is our presentation and it's called the Protopiper. This is our fully autonomous pipetting system that we designed this semester. We're excited to share it with you guys. We have a small group. It's just myself, Devin, and Rachel and Marshall. And so this is our group. All right. So the main goal of our product that we wanted to deliver this semester was to create something that is very easy to use, that is cheap, and that produces reliable results. Our Protopiper performed within the customer specifications very well, and it can also handle a lot of volume ranges all the way down to 100 really. But we are rated for 500 to 5,000 microliters. That was our volume range. Our design really focuses on the streamlined ease of use from the consumer side. And we think we've delivered a case that is very easy to use and easy to assemble. So I'm going to send you to the next slide, and we're going to be watching a operational video on how this product functions, and I'll describe it. Okay, so starting off, we have our case, and we just removed the first half of the case to expose the internal components. This black piece that's going to move up and down is our ejector platform, which is connected to our piston rod. And so moving up will extract fluid, and moving down will dispense fluid. So our piston normally operates and it'll stop right before this tip ejector, which is in white. And that is the standard range. So at the very limit, before it hits the limit switch, is our 5,000 mark. And if something were to happen, it were to keep going, it would contact the limit switch. And we also have a limit switch down at the bottom, and that assists us in recentering after we eject. Okay, so we see it's moving. Now we're showing the ejection process. So as you can see, the platform continues moving down, and it does so by pressing down on this cylindrical tip ejector. So the pipette tip has 360 degrees of contact. So we have a very reliable method of ejecting tips. And as you can see, the way it ejects the tips is it presses down on this spring tab ejector right here. There are two vertical springs. And so after it ejects the pipette, it springs back up to its normal position. So now we're going to show you the simplicity of this case. And I think one of our main selling points is that it opens like a book. And we believe it's very easy to use. So when it's completely unfolded via this plastic latch, we have all of our internal components secured. And the primary way we do this securing of the piston sleeve is by these support tabs right here. So there's 1, 2, 3, 4. And we are able to easily rotate out our entire piston assembly just by picking it up with our hand and moving it over. And so we don't need any screws to get into our case. And these 4 tabs do a great job of setting into these into our milled out cylinder sleeve. And what this does is it allows for extremely easy disassembly of our piston and our sleeve. And so as you can see, we have 2 O-rings that go inside of our piston sleeve, 1 O-ring that attaches to our nozzle, and this nozzle threads into our sleeve, allowing you to swap it out with different size nozzles. So right now we have the 5,000 one equipped, but if you wanted to, you can screw on a different nozzle for the 1,000 range or even the smaller range than that. And then also the piston unscrews from a heat set insert that is in our plastic ejector, and you can quickly take it out. Also noting, all of our screws are installed with a 2mm hex drive, which we provide, and all the nuts are encased in the housing itself, so we don't actually need any wrenches. And I believe over here we can show you we have our Allen key already laid out, and it is right here. So it's provided with the system. Okay, so that's our overall operation. Moving on, we're just going to briefly show you some of the components. One key component here is the anti-backlash nut, which is this brass piece. It's a two-piece system that moves with the lead screw, and it has a spring to provide tension on the threads of the screw, and that allows us to help with vertical stability. Also, to help with vertical stability, we have these 3 rails that interface with the platform, and they really help provide stability as well. Next, we have our stationary components, so the guide rails here, the hex key, all of this good stuff that we explained in the video. All right, so next we're going to be talking about our design of the system, and I'm going to hand it off to Rachel.
Thank you, Devin. I'll be going briefly through the calculations that we used to make some of our major design decisions. Starting with our space optimization, we wanted to make sure that our case was as small as possible without sacrificing any of our performance. So we did an analysis and we found that we would be able to use a 9mm inner diameter piston to reach a height of just about 80 millimeters, which was a range that we could work with in order to minimize the use of material, therefore minimize our cost. And then we moved on to power screw selection, which we compared 2 different power screws, one with a 4mm lead and one with a 2mm lead. We found the cycle time to collect and dispense 5,000 microliters for both lead screws and the resolution that both lead screws would give us. And we chose to go with the lead screw that would give us the higher resolution, which would give us the higher precision in the long run, since our cycle time was well under the customer requirements. And we estimate that we'd be able to handle a 384 weld plate at its full capacity under 2 minutes, giving the gantry team ample time to be able to process moving the pipetter itself. And then we moved on to motor selection, which we had 2 competing motors that we compared, one with a 0.9 degree step and one with a 1.8 degree step. And we again went with the higher resolution, which in the long run, and you will see in our testing, very much lowered our standard deviation in all of our testing ranges. And so we went with the 0.9 degree step motor. Next, we had our plunger design, which we had to estimate a reasonable resolution for our motor. We estimated that we would need to have a maximum 0.157 millimeters per linear displacement per revolution or per step for our motor. And we ended up with a 0.005 millimeter linear displacement per step for our motor. So we wanted to make sure that we chose an inner diameter that would give us a reasonable resolution. Then we moved to O-ring selection, which we used the Parker O-ring handbook for. We debated between a single and double par back O-ring placement, and we went with a double O-ring placement, which we will go into more detail later. But we did use the par back or the O-ring handbook to estimate the gland sizes for our design. And then lastly, we compared backlash mitigation for 2 different nuts that we considered, the regular nut and the anti-backlash nut, which we saw lowered standard deviation by about half and lowered our average error about 1%. And next we have the analysis for infinite life of our lead screw. We chose to rate our lead screw for infinite life because it would be experiencing direct forces, and with the use of our anti-backlash nut, it was creating constant pressure on the threads. And so we were worried that that would create wear in the long run, and it was one of the more costly parts to replace, both in manufacturing time and in material cost. So we found the torque, the raising torque for the lead screw experimentally using a torque wrench, and we used that to calculate the thread stress, which was 0.31 MPa, which was much, much lower than the yield stress of our 304 stainless steel material. And then we did a simple SN diagram comparison to rate our lead screw for infinite life of 1 million cycles. And we had well over 1 million cycles for our lead screw. And lastly, we had an analysis to make sure that we wouldn't create any aerosols using the inner diameter of our piston and also the fluid velocity that we would be getting at 250 RPM, which was the operational range that we came to while testing. And we had a Reynolds number of 71, which is much, much lower than the 2300 necessary for turbulent flow. And here's our testing slide, which shows our method of testing. We chose ranges increasing by 1,000 microliters from 500, 1,000 up to 5,000. And our testing methods allowed us to observe and define independent variables that we would be able to control in our design, mainly our backlash, which we realized was giving us most of our error at the beginning. And we were able to mitigate that through more testing. And another thing we also observed, for example, throughout our testing was drippage outside of the pipetting tip, which we coded in a back and forth motion of the motor to remove, so we would have less error. And in this way, we were able to mitigate error in many different ways throughout the evolution of our design. And below, you can see the correction curve that we used in the coding of the movement of our motor so that we would be able to get accurate dispensing volumes. And here's our final testing data and our results. After having implemented the correction curve in the code, you could see the raw data in gray at the bottom and the blue dotted line that is our desired volumes. And you can see the teal dots that almost matched perfectly with the desired volumes. We had an average percent error of only 0.34% and an average absolute error of only 4.8 microliters. And our standard deviation was very, very good for our lower volume ranges of 500 microliters, but it seemed to worsen as we got to greater volume ranges, for which we would recommend the customer use smaller volume ranges to reach more precise and accurate measurements. And I'll hand it off to Marshall to explain our assembly.
You're muted.
Marshall?
Sorry, I apologize. When concerning the assembly of our product, one of the main factors we went with the bookcase design was for ease of assembly. And so the assembly times are pretty short. In order to access the piston by removing the sleeve for lubrication and replacement of O-rings, that can be done in a matter of seconds. And our out-of-box assembly, which is most important for the customer needs, was 5 minutes. Also, looking at the lubrication and seals of our design, proper lubrication over the moving surfaces was a really big component. Too much lubrication or too little would ruin the performance of the system. And like Rachel said, we did use the Parker O-ring handbook to determine gland size and depth, so that our O-rings would last all the way through testing. Another factor of our assembly that is important is that the simplicity of the assembly and disassembly. Like Devin mentioned, we do have a 2mm hex key that can be used to remove all of the bolts. And with inlaid nut housings, there's no need for a wrench. Looking at the cost of our product, the bill of materials, we are under the $100 mark, a total of about $86. Some of the main factors, big costs were the NEMA 17 motor, about $20, the tool plate assembly, and the 9mm piston steel precision ground rod. Also, a big component that helped us with accuracy and performance was the anti-backlash nut, which is only $6. So looking at the design evolution of our product, we went through many different iterations and about 5 different versions. We started off with the book design for, like we already explained, easy maintenance and all of that. And we also used we optimized the tip dispenser design, going from a double to single ejector tab to reduce the amount of parts needed. And then we also explored how to better how to better improve the vertical motion, the linear motion of the piston by using adding rails into the case, and also using a bearing at the top of the lead screw to prevent precession of the lead screw. We also added, obviously, that anti-backlash nut and a flexible coupler to attach the lead screw to the motor shaft to decrease the axial misalignment. As you saw, we did test multiple motors. Main reason for the motor that we went with was due to the fact that it had a detachable wiring connector. The original one, the wires were sent straight to the back of the tool plate and soldered. So having that detachable wiring connector helps for disassembly. And then finally, looking at the case, we originally used metal hinges and a latch, but we ended up printing our own and integrating those into the case. So here's some of our iterations going from the left, and it was our very first version, moving all the way to the right to our last prototype. You can see that the walls actually, the thickness of the walls of the case decreased almost every version. We also added more rails as we went along to stabilize, and we added the limit switch supports in it. Also, we had to put in holes and wire catches for the attachment of the wires to the tool plate. Looking at the top, you can see our ejector platforms. The first design, we actually were using a plastic piston, and we decided that that was not going to get the job done. So we went with a heated threaded insert into the ejector where you'd screw in the piston. The size and geometry of the ejector changed over time. That way it was easier to swing out of the case for disassembly. So we already talked about ways to mitigate error in the design aspect, as Rachel said. Obviously, the use of that anti-backlash nut, and then using the proper O-rings and moly-coat lubrication was very important in the performance. And then also those stabilizers, the use of rails, flexible coupler, and the case-supported bearing for the lead screw precession. Okay, looking at the customer needs, we met all the customer needs. The BOM is under 100. We satisfy the dimensional weight requirements. Mainly our flow rate requirement was satisfied, and which also prevented creating aerosols or backsplash. We are able to deposit the fluid within the range and accuracy, and we can eject the disposable pipette tip without cross-contamination. So this is our accuracy demonstration. Our goal was 715 microliters. And we used a high precision scale to receive a test result of 718.4 microliters, well within the range of accuracy needed. I'm going to hand it on to Devin.
Yeah, okay, great. Thank you. So that's the majority of our presentation. So now we're going to talk about future improvements. So if this design is selected, we think it still needs work on one issue with our design, which we believe is kind of a floating accuracy. And the best way to describe this is we would perform our testing procedure by starting out with a cold motor and applying current and basically leaving that current on, because we found that through testing a cold motor wasn't great, so we wanted a warm motor. The problem that we're realizing now is that the stepper motor is highly dependent on the temperature that it's operating at. And the longer the current is going towards the motor, the more it's heating up. In our original motor, we had a very heavy, high torque motor, and we didn't really notice any issues with it. We were able to get pretty repeatable results after the motor warmed up. However, when we switched to the 0.9 degree per step motor, it was about half of the weight, if not more, and half of the torque. And that motor we noticed heated up quite a bit more and a lot faster. And so the problem we were running into is we would run our calibration, which was about 60 tests. We do 10 at 500, 1,000, 2,000, 3,000, 4,000, up to 5,000. And using those 60 points, we would create our calibration curve. So the problem we ran into was, after we ran this, and we would say, all right, let's go back and try and get 40. We would, or let's do 4,000 degrees or microliters. We would run it and get really good precision, again, always within about 1 to 3 microliters, but our target accuracy would be off by like 10. And so what we realized is we were testing each of these volume ranges at a different temperature pretty much every time. And so it became this kind of frustrating chasing of, we're getting really precise results, but our accuracy is a little off. And we only really made this thermal connection like, not very long ago. We kind of put the pieces together. So solutions that we came up with to remedy this is, first and foremost, to keep the motor at a constant temperature. And I think a simple feedback loop with a temperature sensor on the motor would do the trick. So we would measure the temperature of the motor, and if it's increasing past our set point, we would instruct the Arduino to just cut the voltage to cut the power to that motor while it's idling, and let it cool down. Once it was cooled down to the temperature we wanted, we could apply the current again. And doing so would allow us to test all of our volume ranges at the same temperature. And we also found this true when we were testing by ourselves, because when we would come in and test by ourselves, we wouldn't be talking to anyone. We would do all of our volume ranges like really quick and find that, they're all very accurate. But when there was like 3 of us there and we would test, we'd be talking and whatnot, the motor would just be getting hotter and hotter, and we'd lead to these problems. And the second method is to create a temperature true angle calibration curve. And basically that would be measuring the shaft angle compared to the commanded rotation in Arduino and plot that against the motor temperature. And therefore, if we had that temperature sensor, we would know how far off the angle is from what's being commanded. Say it was supposed to rotate 11,000 degrees and it really only rotated 10,980 degrees. Well, that represents a bias error in your design. It'll still be precise, but the accuracy will have shifted. And so if we know the full range of our motor, then we could properly counteract that. All right. Yeah, so those are our main talking points. And I want to thank you very much for coming to the presentation, and we're going to open up for questions now.
Let's see if Rick wants to go first today.
All right.
Maybe not. All right, well, I'll go ahead and go. This is Tom Singer from Northrop Grumman. I want to start off saying the video that you guys had in the very beginning was fantastic. That was kind of the best demonstration of the operation of your system that I've seen personally. I've missed a few of these, but I've seen a few more, and that's the best one I've seen so far.
Thank you.
Yeah, no problem. I really appreciate that. I like that you've got your motor and your lead screw off axis from your plunger, which is not the most structurally efficient design, but it seems like it's well supported in the box, and so I appreciate that. It shouldn't rack significantly. I think you've got it well restrained against that rotation, so you won't have any problems. I don't expect that you have any problems actuating the plunger or with like excessive wear on your components with that. So I like to see that. I wanted to ask why the motor is external to your box here.
Sure. We kind of, because it had a nice spot to fit in. That was kind of the thinking here. We wanted to really cut down on the height profile. Also, we wanted to be able to quickly disassemble a motor, and it's really just attached with 3 bolts, and so it can come out quite quickly. It was just kind of a spacing thing. We kind of wanted the whole system to look like a rectangle, as opposed to if we're housed inside the box. Yeah, I don't know. I guess we didn't really consider that initially, but it's something we could consider if the customer deemed it valuable.
Yeah, it's interesting that the rest of the system is kind of contained within this nice clean
Right.
box. And yeah, the latch here, is this sort of like the just like a snapping kind of latch, or like a lever action kind of latch?
It's a lever action latch. I didn't
Okay.
actually animate it, but it basically opens up. Let's see, what would be the appropriate analogy? So this tab right here moves over, which causes this bottom clasp to shift outward, and then
Okay.
like a toolbox latch is basically what it is.
Yeah. Okay, I like that design. Let's see, I like, man, I'm just like going on about how much I like things in here, which is unusual for me.
Thank you.
I like that you're thinking about, when you got to meet your dispense time, right? You said we can dispense however many microliters of fluid in 2 minutes, which gives the gantry time, or the gantry lots of time to move around and service the well plate, right? That shows you're thinking about things meeting customer requirements as a complete system, right? That you don't have a requirement that your pipette has to meet, you have a requirement that your microbioreactor has to meet, right? So you're thinking about that sort of thing. I'd like to see sort of that interface of how quickly is the gantry actually going to service, right? You're saying, hey, that should leave them plenty of time to do it, but what is feasible for them, right? I mean, it might be that that's not enough time for them to do it, and that overall as a system, even though you think you're good, that you don't overall meet the customer requirement.
Right.
But I do, you're starting to think about how your system fits within the larger device. When you were talking about the lead screw, and I don't really think there is a significant concern with the life of the lead screw, but since you did the analysis, I'll pick on that a little bit. I think you were looking at like shear of the thread. Is that what I remember? Oh no, okay. So you like
the
bending and
analysis was
shear
based
of the
on-
thread?
Yes, it was based on of the von Mises stress that would be experienced by the threading itself. And the normal force that we calculated came from the torque that we experimentally found using a torque wrench to create the raising torque of the lead screw of the entire platform.
It's not something that I think is going to be big. And again, I don't expect this to be anything close to the overall life limiter of your system. But when you're looking at a threaded rod, those threads are going to create stress concentrations, and those stress concentrations are going to magnify the actual stress that you see and promote cracking. So that's something to think about there. Again, I don't think that's a major concern, but if you're going to show the analysis, I think that's an important part of it. Then when you were looking at your calibration stuff later on in the there it was right there. It seemed, man, what are the units of your absolute error? Is that microliters?
Microliters, yeah.
Yeah. What's driving 40 microliters of difference and of variability at 12,000 degrees?
Yeah. So what ended up happening was, so you're right, we do have that off-axis system, and even though there's not very much backlash right now, because we've mitigated a lot of it. Initially, there was a ton of backlash, and you could quite literally see, the motor would be going and just lifting up one side of the platform, and then there would be lag. And we mitigated a lot of that, but it's really difficult to determine what exactly is causing the difference in absolute error. It could be due to I don't know, machining tolerances of the piston rod, or I personally believe it has to do with the motor that we're getting these inaccuracies, because all honesty, it was a pretty cheap motor, and if it's off by a little bit, we see quite a substantial amount of absolute error change, and so we had a tough time like figuring out why it was off by 150 microliters. And we really didn't get a full answer to why that was, but the best we could do was just come up with a calibration curve for it to mitigate something like,
Yeah.
as much as we could. But obviously, if we had a lot more time, that's always something that bugged me why it was off like that.
I'm not so concerned about the absolute error. I think that's something you can account for
Right.
with calibration, like you said. But that 12,000 degree rotation where there's a variability of, on the order of
This right
40
here.
or so microliters. Yeah, that just
Oh,
seems,
yeah.
yeah, it seems like a lot.
Yeah. Right.
While we're talking about this, and I haven't asked anybody this before, you have a dispensing accuracy criteria for your customer, right?
Yes.
Do you have
yeah.
I don't know the technical term for this, so I'm just going to call it, do you have a sucking accuracy criterion?
I don't believe so. Like a pressure vacuum that's supposed to be created.
Well, no, I mean, in terms of you're dispensing fluid, but you're also like extracting fluid, right?
Oh, like the rate
Yeah.
or I don't believe we have a rate. It was just the only constraint we had was volume flow rate coming out.
Yeah, I would be interested to know if the customer, given the way the customer wants to use this microbioreactor, and again, this is sort of a systems thinking and an applications kind of thinking. If the customer expects to be able to extract a certain volume, to say, hey, I've got a cell or a dimple or whatever in my well plate, and I want to pull out 50 microliters or 100 microliters of fluid. How accurately can you do that?
Without dispensing it after? Or
yeah, just to extract that much from a given well plate and put it somewhere, do something with it. I'd be interested to know if they have any expectation of doing that, and then if they do, what the accuracy of that would need to be.
Sure, you're right. Yeah, no, I believe they just gave us plus or minus 10. So I was kind of assuming it was all right if we're extracting 1,000 microliters, and when we dispense it again, it has to be within either 1,010 or 990.
Yeah.
I just kind of assumed that's how they were going about that, but that's
definitely it's kind of
something we could figure out.
It's a different thing if you're like pulling 1,000 microliters out of like some tank, right? A nutrient tank or whatever. It doesn't matter quite as much how accurate that is. But if you're extracting from your samples, that might be something more important.
Well, they also didn't give us a restriction on media either, which is something that I would think would make a big difference depending on the viscosity of whatever liquid.
Viscous it is, and
So all these tests were conducted using water, I'm pretty sure most of the groups did that as well.
Yeah, and that's probably a pretty reasonable analog for anything that they'd be using, but yeah, maybe a good question to ask. And the one other thing I'll ask, and I don't think I asked anybody else this, the calibration that you're doing, right? That's at you mentioned effects of the motor temperature on how accurately you're dispensing. Did you consider effects of the overall system temperature?
No, not really. Just because it was, the whole enclosure was in a pretty well ventilated lab, so the temperatures in there we didn't really measure with a thermometer or anything, but they didn't seem to fluctuate all that much. I guess it could have been
you're riding
the motor
around
from the
in
temperature. Yeah.
You're riding around in a chamber that's environmentally controlled, right?
Yes. And the way we would approach fixing that was the true temperature curve that Devin had mentioned before, where our motor would be calibrated to its temperature conditions to try to get the most accurate volume possible.
Well, I think he's referring to like the enclosure.
Need to add consideration. Yeah, if the enclosure is at 70 degrees C, right, you may need to add consideration for that impact. And I'm envisioning like your cylinder's growing, right? So if your diameter is growing and you're traveling the same distance, right, you're dispensing more fluid. I don't have a great sense for how impactful that'd be, but maybe something to consider.
Yeah, I agree. And that's something we could definitely test once the enclosure is up and running. We could put it in and run the same type of tests just at a controlled environment and see what what it was coming out to, but we didn't have that kind of testing apparatus available to us.
Yeah.
So this is Rick Miles at Northrop Grumman.
Hi, Rick.
I've got to say I really appreciate your presentation because I was actually on a work call at the same time you guys were presenting, so I didn't get to hear your entire presentation. But yours is the first presentation where I thought I could follow along on all your design without actually having to hear you talk, because you have things very well denoted in your slides. And the video presentation was really good. So I mean, it was really excellent. I love the way that the layout of the presentation was. It was very easy to understand. And I think someone that was a layman and didn't know what was going on here could easily pick up and understand what you're trying to do. So excellent job.
Thank you very much. We appreciate it.
Hey guys, I wasn't joking when I just dropped into the chat, saving the best for last. So also,
Yeah.
just so Rick and Tom can know, this group had half the number of group members as most of the others. So they were undermanned the entire semester and were rock stars the whole semester.
Yeah, did a very good job.
Thank you.
All right, well, gosh, if you're gonna build them up like that, what are you guys doing putting a hex key in here? Like this is like the IKEA of pipetters.
That's true.
I think that's the hex for the fasteners to take the motor out if you need to service the motor.
Yeah, no, I know that, but
Yeah.
from a material standpoint, right? You're designing things to live in a like 70-degree humid environment, and I'm pretty sure at least most of my hex keys at home are not going to be real happy with that, unless you're speccing some like high-strength stainless hex key here. I can't imagine that that's gonna not rust and potentially contaminate experiments. It's also gonna get lost the first time anybody uses it. It's not gonna get put back.
Yeah.
I appreciate the intent here, but I think that's maybe not as helpful as you might hope it would be.
Right. Oh, thank you. Yeah, definitely did not even consider the temperature change on that for sure. But yeah, maybe we can give them a little plastic baggie or something to hang up next to it. I don't know, something to keep it safe.
Put it on the outside of the box, and it has a better chance of surviving, but it's still going to get lost.
Yeah, that's probably true.
I can actually say that I don't think the lab I did my PhD in had a single 530 seconds hex key. We had 20 Allen key sets and there was no 530 seconds Allen key in the lab. I had one that I duct taped under my desk.
Wow.
To keep other people from stealing it because it was the only one available.
Yeah, we were always scrambling for the 2mm in lab.
Yeah.
So we were like, just always have it.
There was one 2mm drive that had like the screwdriver end at the end of it, and that was always gone. So I understand the struggle.
So, all right. Well, I think we're going to actually wrap it up on that note. We went a little bit long, but it was, there was great discussion and great feedback at the end of the day here. So thank you guys. Congrats. Again, you guys were absolute rock stars all semester. You kicked ass today. Way to go. Congratulations. You're free for the most part. Just a little bit left to go, but the rest of the week is yours. Just congrats again. Way to go, guys.
Thank you
very
so
much.
much.
Yeah.